So here's the left endpoint approximations. Here we go. Okay, so the graph, this one looks like, if we draw the same graph, then we have something that looks like that, and then we have for from A to B, okay, and then we had some kind of intervals going on here, all right? So, but the important thing from this one is to recall, so this is A plus delta x, A plus 2 delta x. Sorry, it gets kind of squished in there. That one refers to that, and that refers to that. And then from A to B, but now when we draw our rectangles, we're using the left endpoint, the value of the function at that left endpoint, to be the height, to give us the height, instead of the right one. So see here how the right one would normally give us a short rectangle, but now if we're using the left endpoint, so in this case that would be A, f of A, it would be a little bit taller, okay? So this is what's basically happening with the left one. And then for this rectangle, for example, we would just end it here, because that's the left endpoint. This one would end up here, which isn't too much different, and this one would end up over here, okay? So anyways, so that's what left endpoint looks like on a graph, and formulaically, what we have is that A, our first endpoint, is going to be A plus 0j, or 0j, 0 times delta x, okay? Because that's basically just saying A. This is equal to A. That's our first endpoint there. That's our left endpoint. Our next left endpoint is A plus 1 delta x, okay? And then et cetera, until we get to this final one, which is not, because B is equal to, remember we said that's A plus n times delta x, but this is the right endpoint. We don't use that one at all. It kind of just gets ignored at the end. We end up with our last left endpoint is A plus n minus 1 times delta x, okay? We end up one short of that n because we don't use the rightmost point there when we're using left point approximation or left endpoint approximation, okay? So that means that our j ranges from 0. So here's j. J ranges from 0 up to n minus 1. All right. So for L sub n, our left endpoint approximation, we're going to get the same exact thing. So delta x times the sum of, but this time j starts at 0 and it goes up to n minus 1. But we have the same formula in here. So f of a plus j times delta x. Okay? So that's for the left endpoint. And lastly, so we did right, we did left, and now we'll go on to something different, and that's called midpoint approximation. So here's the midpoint one. So we're going to do that one now. Alright, so graphically, this one is going to look like the following. So we have x and y. Here's our graph, let's say. It's a little bit different. So here's A and B. Here are intervals. I'll just draw it really quickly. And then let's say we have our intervals are divided like this, okay? Actually, I'll make them a little bit wider so we can see. So I'll just do big ones, big intervals, okay? So now, on an interval, we're not picking the left endpoint or the right endpoint. We're picking smack in the middle, okay? And then that is where we're evaluating our function to give us the height for that rectangle, okay? So this one's going to look like this. The middle point is going to give us the height of our function. So here's our next interval. We're going to pick right in the middle there, find the height of the function there, and make our rectangle. And for this last one, it would look like the following. We go straight up, find the function, value of the function there, and make our rectangle. So this is midpoint approximation, all right? And so for this first one, it's not an endpoint anymore. It's called the midpoint, right? So here's, for example, on the x-axis, here's A, here's B, A, B, right? And then let's say this is our these are our intervals. So this is A plus delta x. This is A plus 2 delta x. So right in the middle between these ones, this point here is called A plus 1/2 delta x, right? Because we only moved half of a sub-interval. So this is our first midpoint, okay? Our next midpoint would be A plus 3/2 delta x, right? 1.5 of them. And then so on and so forth until we get to A plus n minus 1/2 delta x, right? Because then at that point, so this is, let's say, okay, I'll draw one more. So A and B, okay, so we have A, something, something, something. Here's B. So let's say this is our last endpoint, or our last interval right here, okay? So this is A plus n minus 1 delta x. And this one here is equal to A plus n times delta x. So this one is going to be not n minus 1 or an n. It's going to be, this point is going to be A plus n minus 1/2 of that delta x there. Okay, because this is like a 1/2 delta x. Anyways, okay, so what the formula is going to look like for our midpoint approximation is the following. So we're going to have m sub n is equal to, so we still have that delta x in there, and then we have our sum of, and we're going to say j equals 1 up to n. So this one is basically like, it's set up in the front like a right endpoint approximation. But now what we're going to have is something a little bit different. So then we have f of a plus, and now we have j minus 1/2 times delta x. Okay, so I got a little squished in there with the number line, but I'll rewrite it on the next slide. Okay, so again, the formula for our midpoint approximation is m sub n is equal to delta x, and then we have sum of j goes from 1 to n of f of a plus, and now we have our j but minus 1/2 and then delta x. Okay, so just that factor of minus 1/2 added in there. Okay, all right, so let's do an example. So we're going to calculate L sub 6 for f of x is equal to x to the negative 1 power on the interval 2, 4, on the closed interval 2 to 4. Okay, so let's see what we have going on here. So L sub 6, so our n is equal to 6. So we're going to make 6 sub intervals basically, all right? And then here's our f of x, and then this is our interval, so this is a equals 2, and b is equal to 4, all right? So let's set that up. Let's recall our left endpoint approximation formula. So that's L sub n is equal to delta x, okay? And then we have sum of j starts from 0 and goes up to n minus 1, right? Because we're doing the left endpoint there. And then we have f of a plus j times delta x. Okay, so first of all, let's figure out what is delta x. What is the length of our subintervals here? So that's going to be the length of our full interval divided by the number of subintervals. So that'll be b minus a, so that's 4 minus 2, divided by n, which is 6. So that'd be a 2 over 6, which is equal to 1 over 3. Okay, so we figured out what delta x is. That's 1 over 3. So then we can plug in some things. So we have L sub 6 is equal to 1 over 3. And then we have j starts at 0, and then it goes up to n minus 1, which is a 6 minus 1, so that's 5. Okay, and then we have f of a, so that's a 2 now, plus j times delta x, so plus j just stays there because that's a variable right now, and then delta x we figured out to be a 1 over 3. Okay, so now let's see what happens here. So from here we have L sub 6 is equal to 1 over 3 times the sum of j equals 0 up to n minus 1, which was a 5, and then f of 2 plus j times 1 over 3, okay? So what do we do now? What does this mean? So remember that this symbol here means sum of, and then this denotes our formula for the terms to be added, okay? And then remember that our f of x is equal to x to the minus 1, which is the same thing as 1 over x, okay? So basically what we're going to do is expand, all right? So this 1 over 3 can just stay in front. That's just out there, right, and outside of everything. So this means what we're going to do is say f of 2 plus, and j starts at 0, so 0 times 1 over 3, okay? And then we're going to add that to, so we're taking the sum of, so we're adding terms, f of, and now we'll put in the next whole number, which is a 1 for j, okay? And then we have a 1 times 1 over 3, plus f of 2 plus the next whole number is 2 times 1 over 3. And we're going to keep doing this until we get to a 5 in for our j. Okay, so f of 2 plus 3 now, 1 over 3. Okay, and then we're at f of 2 plus 4 times 1 over 3. We're almost there. And we have one more term, f of 2 plus 5 times 1 over 3. Okay, I think I have enough parentheses there. Just kidding, I need one more. There we go. Okay, so this is what we have, and now we can just like add all of these numbers inside and see what we get. So L sub 6 is equal to 1 over 3 times f of, so this 0 term goes away, so f of 2 plus f of 2 plus 1/3 is going to turn out to be a 7 over 3. Okay, and then we have f of 2 plus 2/3, that's going to be an 8 over 3. The next one is going to be a 9 over 3, which is the same thing as 3. The next one is going to be f of 10 over 3, And the last one is going to be f of 11 over 3. Okay, so we have 6 terms going on here. And now the thing that we're going to do with this is plug these values into our f function. Okay, so our f of x, which is x to the minus 1 power. And we'll do that on the next slide. So we have, let me try to fit it all in one line here so we can look at it pretty easily. So f of 2 plus f of, and the next one was a 7 over 3, plus f of 8 over 3, plus f of 9 over 3, which was 3, and then we have a 10 over 3, and finally an 11 over 3. Okay? So if we plug all of those in, we get 1 over 3. So basically what our function is going to do is we have, so f of x is equal to x to the negative 1. So that just means flip your fraction, whatever you plug in. So for this first one, we're just going to get a 1 over 2. And for the next one, we get 1 over 7 over 3, which is a 3 over 7. And then the next one, we get 3 over 8. Okay? So we see a trend here, 1 over 3. We're just going to flip the next one, 3 over 10, plus 3 over 11. And here I'm just flipping them because that's what our function told us to do. If it told us like x squared, then I would just square all these values, and etc., etc. Okay? So this is going to turn out to be, this approximation turns out to be a total of 0.737. Okay? And that is it for that problem.